Thanks for that brilliant introduction. As mentioned, yes, I'm Andrew. I'm a first-year PhD student here at the University of Exeter, supervised by Dr. Yang Liu, Professor Gavin Table, and Dr. Sham Prasad. And I'm going to be talking you through today some of the work I've been doing on CFD modelling microrobots in the gastrointestinal circulation, with a view on using our results for gaining an understanding in metastatic cancer detection. So first off, I'll just quickly run through what we're going to be talking about. I'll give you a brief overview on metastatic colorectal cancer. I'll then talk a little bit about why we might want to use computational fluid dynamics to model this problem. I'll then talk to you about our research question, what we're trying to answer. I'll talk about the use of OpenFOAM CFD code. I'll show you a quick result, and then we'll conclude the talk. So just a really brief nutshell on what metastatic colorectal cancer is. What we're talking about here is really when a primary tumour in the colon, or the large intestine rather, gains a certain size and a certain development, some of the tumour cells actually break away from the primary tumour and invade through the local tissue, and quite often encounter surrounding blood vessels. And then through a process which we call intravasation, these cancer cells can actually make their way into the blood vessels and circulate in the circulatory system. We then call these circulating tumour cells. And with regards to colorectal cancer, the liver is actually one of the most common sites of secondary tumour development. And that's thought because of the portal venous system here. When these circulating tumour cells do reach the liver, they can bind to the cells of the blood vessels locally, and then through a reverse process of intravasation, leave the blood vessel and create a metastatic colony in a different site. Second, why might we want to use computational fluid dynamics for this problem? Well, first off, blood is a fluid, and historically, CFD has been used to analyse complex flows between fluids and solids, and even fluids and gases. It's frequently used in the aerodynamic and hydrodynamic industry, really to save money and time before costly prototype or experimental testing. And I know when I think of computational fluid dynamics, these type of images come to mind, of cars and motorbikes. But in recent years, CFD has been seen to be quite a powerful tool to model blood flow. An example of this would be in an artery here. So now on to our research statement. What do we really want to solve here? So we want to model the local interaction between the fluid, in our case the blood, and the solid, in our case the microrobot, at the boundary of the microrobot. And by that we mean we want to really assess the influence the fluid forces, the fluid torques, and the environment affect the microrobot's dynamics at a local scale. And we also want to be able to apply magnetic forces and magnetic torques to our microrobot too. So we've used a special resolved CFD DEM code written and developed by Isos and Surek et al. And implemented into the open source CFD code OpenFOAM. In its basic form, that code, it really solves the resolved forces and contacts of suspended particles in fluid. And these are the equations we're looking at. So the Navier-Stokes equations, they describe the motion of fluid in our computational domain. But what's special about the solver we're using is this added forcing term S here. And this basically describes the forcing term on the immersed solid we're looking at. So in our case, the microrobot. And this is given by the indicator function here. So it's 1 when a cell is representing a solid, and 0 when a cell is representing a fluid. But like I said, the original code only solves for the particles suspended in fluid. So we want to add in the magnetic forces and the magnetic torques we can apply to our microrobots. And I understand on the great talks before, this was shown in detail, so I'll keep this quick. But these are the magnetic forces we're applying. Of course, the volume of a microrobot, the magnetization, and of course our gradient magnetic field will apply. And likewise for magnetic torques, we have the volume again, our magnetization, but this time cross product with our uniform magnetic field we want to apply to our microrobots. And this is the behavior we'd expect. You saw this earlier, I know, but the microrobot would accelerate in the direction of our gradient fields, and align its magnetic moment with the uniform magnetic field, just like a needle on a compass. So in our simulations, here's a free body diagram describing the forces and the torques we see on our microrobots here. So like when we set up our CFD simulations, we define the inlet and outlet boundary conditions. These are usually for, velocities or pressures, or a combination of the two. And of course, from that, we have the fluid drag force acting on the microrobot, the combination of buoyancy and gravitational force acting on our microrobot, in addition to the magnetization force we talked about a little earlier. Again, with regards to the torques acting on our microrobots, we have TF, that is the torque the fluid exerts on our microrobot, and TM being the torque of the magnetic fields that were applied to our microrobots too. So you can see we've just added these forces and torque into their respective Newtonian equations of motion, so the acceleration and angular accelerations respectively. For an open form, just two little figures showing the proof that the code's working really. On the left, you can see an ellipsoid-shaped microrobot initially aligned with its magnetic moment along the x-axis, and you can see it's aligning its magnetic moment with the direction of our uniform magnetic fields we've applied there. Likewise, with our figure on the right, we're seeing a spherical, I guess, bead pulling gradient microrobot accelerating under the magnetic actuation force supplied by our magnetic field gradient. It's also worth mentioning, before the whole setup of these CFD cases, we can obviously specify the magnitudes and directions of our gradient fields, our uniform fields, and of course the magnetization, the volume of the shape of our microrobots we want to study too, in addition to the normal boundary conditions that we'd want to set up for our CFD case also. So how's that useful to us? Well, as engineers, we can use these CFD results to optimize the size, the shape, the magnetic composition of our microrobots, in addition to both the field strengths and field orientations of our external magnetic fields that we want to apply to these microrobots too. All in all, really, to model the motion of our microrobots in complex flow conditions. And an example of that would be in the arteries with pulsatile flow. So here, really, we've got some just some little test results that we're going to show you, showing what we might want to actually model here. So the graph on the left here, which shows the velocities over time of a small spherical microrobot of diameter 400 microns, actuated under a gradient of 100 millitesla per meter into a blood flow, against a blood flow of 10 millimeters per second. First, we did run the simulation without blood flow, and then we ran it with blood flow. So you can see the difference in the terminal velocities there. Likewise, with the little graph I have up there on the right, it's showing the same simulation. Firstly, the microrobot moving in the center of the channel against blood flow, and then the microrobot moving offset from the center of the channel by 200 microns. And you can see how we've utilized the fact that the blood flow velocity close to the wall is lower than the streamwise velocity in the center. What about biomedical applications? Because obviously we want to apply this to our biomedical application with gastrointestinal circulation too. So we can actually acquire CT scan files and generate 3D geometry of the blood vessels we're interested in. And from there, we can actually create a computational mesh to be able to run our CFD analysis on. Then, of course, we can apply our boundary conditions and then run the analysis and post-process too. So this is exactly what we've done here. Just two videos showing similar simulations of the spherical microrobot being passively transported through a bifurcated blood vessel, taken from patient-specific CT scan data to build up this geometry. On the left is a view from actually inside the blood vessel, and on the right is a view from outside the blood vessel. And you can see how this could actually be quite a useful tool for maybe trajectory planning or path planning. Next, we've got to look at future work and the outlook of this project. So first off, obviously it would be very useful for us to experimentally test, but with regards to the computational model we have at the moment, I'm looking at maybe implementing the deformable particles. These would probably come as the constituent cells of the blood, so both the red blood cells and even the circulating tumour cells we talked about at the beginning, in addition to realistic behaviour of the deformable nature of the blood vessel walls. So all in all, we'll use these changes to really study the dynamics of our microrobots to give us probably a helpful insight into the potential of colorectal cancer metastases. That's the end of my talk there. Thank you for listening. If you have any questions, I'll do my best to answer. Thank you.